Hello, everybody. Welcome to our AP Pre-Calculus notes for 1.5. There are, what a way to start. We're already in the dark. Wave your hand like you just don't care. We're here to start 1.5 day 1 here in AP Pre-Calculus. Coach Weidenbauer, don't forget, like and subscribe. 1.5 is pretty loaded. It's got 3 days worth of stuff, so let's get to it. Here we go. So just sketching polynomial functions. That's all we're doing today, which is a really awesome first. We're going to start talking about limits, talk about end behavior, and a lot of this stuff. Like if you get a good hold of 1.5 day 1, you can really use this to carry you pretty far into this course for a lot of the expectations are. So big day today. Big day. All right, let's talk about even degree functions, which is not the same thing as even functions. Even degree functions can be different from even functions. So even degree functions have end behavior at the same direction. Okay, so our most popular, and I'll kind of draw it for us, our most popular even function here is our good old friend the parabola. I guess I'll do this in pink. It looks like that. Our good old friend the parabola looks like that, or that, which is x, some sort of x squared. And as you notice here, our behaviors, our end behaviors are the same. Okay, so the end behaviors are in the same direction. They both go to positive infinity if my a value says a value. If our leading coefficient is positive, okay, leading coefficient is negative, and they're both going to end up to negative infinity. And we'll get to draw this to make more sense of this. I even got some pictures down here to show you as well. Odd degree ones, the most popular odd degree one, I guess I'll do this in blue, is a linear function like this. Those are odd degree functions. You can notice that the end behavior is opposite. If our a value, so our leading coefficient is positive, we're going to end up equaling positive infinity on the right side. That's our right end behavior. And then if our a value is negative, then our right side will end up being negative. Okay. A couple more things here. And this chart is really important for you to know. This doesn't have any actual limit notations on there for this little chart, but this is going to kind of help us out with, hey, I have two different versions of odd. If we have a positive coefficient here, so for this odd positive coefficient, graph's going to look something like this down here. Okay, you can see the end behaviors. Opposite. Odd, opposite. Pretty easy. The other odd one that has a negative, if you notice here, that right end behavior is going to be negative. I'll circle this other right end behavior. The right end behavior is going to go with our coefficient. Okay, always. And then for this even degree one right here, if we're positive, my right end behavior is positive, and actually so is my left, the same direction. Again, even negative means our right end behavior is going to be negative. We're both going down there. Okay. So this is what we're going to do. Determine if each graph represents an odd degree function or even degree function. Describe the end behaviors. We're not going to go technical yet with limit definitions, but we'll just look at this thing. Okay, for A here, what's our degree, highest degree? Very good, it's 4. We're degree 4, and our A value is equal to 1, which is positive. So real quick, I like to just do a little bit of a sketchy poo. So our function here has the same end behavior because we are even. 4 is an even number. So our right end behavior is going to be positive. I'm going to put a plus infinity. And our left end behavior is going to be the same because it's even. Okay, so right and left are the same because they're even. Why are they both up? Because the a value is positive. So the next one, I'll do this one in purple. For the letter B, it looks like we're here at a degree 5. And what's our a value? Very good, class. -1, which is less than 0. Okay, so this is going to be odd. So it's going to be odd, and then negative is the right end behavior. A lot of stuff going on in the middle. I don't really care. I just care about the end behavior. Okay, these are supposed to be arrows. This is not good arrows. Okay, so what's the right end behavior? It is negative infinity. You can just tell from my picture right there. Left-hand behavior should be opposite of the right-hand behavior because we're odd, and that's going to be positive infinity. Next one here. So this is a little bit different on how to count these degrees. Okay, what makes this one so fun, so different, is everything we've had has been in standard form, which means that we've had all of our powers, our terms being added or subtracted. This one has factors. So what you're going to do here is you're going to distribute this all the way through and solve for this. No, you're not. That's too much work. We're not going to do that. Whenever you have factors, you can actually count each factor and add them up to tell the degree. So if you were to add up the 3 and the 2, you get degree 5. Okay? We're degree 5 here. All you do is add up the powers of the factors. Super simple. And then what's the a value? Well, first off, look inside here in front of the x's. Okay, those are both 1. So 1 cubed is 1, 2 squared is 1. They're going to be just 1. So the a value is 1, which is positive. Okay, be careful. Be careful. For some reason, I have like 4 minus x instead. That's actually going to be a negative x right there. So we just need to be careful in this situation. So that'd be a negative x. So that would change the a value to be negative. Okay. So I'm going to, don't know what just happened. Me and technology don't get well together. Okay. So with this information here, we are odd positive. So right end behavior is going up. Oh, me and drawing. Okay, so right end behavior is going to be positive infinity. Left end behavior is going to be negative infinity. Got it? Questions? You can't. It's a video. All right, so by looking at these, what's all we're going to do? Determine if each graph represents an odd degree function or an even degree function. And we're going to list how many real zeros there are. The zeros, just a reminder, are going to be x-intercepts. X-int. That's when it crosses the x-axis. Okay. So for the first one right here, I have different end behavior. So since I'm different, I must be odd. And then how many zeros will cross the x-axis there, there, and there. So it's going to be 3 zeros. Okay. For the second one there in the middle, those that go the same way, they're both positive. So this is going to be even. And I don't see any x-intercepts. There are 0 zeros. Try the last one on your own. Did you get even? That's what I got too. Did you get 2 zeros? That's what I got too. Why is it even? Very good. It's even because and behavior is the same. They're both negative. And then I can count 2 zeros. 1 there, 1 there. So 2 zeros. Easy squeezy. Let's get to something completely new for you. Try not to scare you here. Describing a function using limits. Now, we've just been kind of just generalizing the end behavior. We haven't actually used limits to describe them. So this is what this looks like in terms of notation. Okay. So I'm going to do something kind of fun here. Remember back in the day when you first learned to draw, or not draw, when you first learned to write, and like you had to learn like how to write the letter A and see how the letter A is like half the size, but then the capital A is like the whole size, right? And the letter B. Remember writing that, doing this stuff back in the day when you first learned? I'm going to do that right now with you with limits so that you can learn correctly how to write a limit. Okay? And I'll do that right now. So the limit, I always use a cursive L because I don't like using a non-cursive L because I confuse my non-cursive L's with the number 1. So I'm just going to use, and what I do is I put it like this. Limit. And then just below that, x approaches wherever I'm going. Let's just say I'm doing infinity for right now. Okay, so that's what I do. And then I put f of x kind of right in the middle. So if you notice, I put my limit kind of in the middle, and I put my f of x kind of in the middle. I just put my x approaches infinity in the bottom. So that's just kind of how I do it. Actually, that's not really how I do it, but that's a good example for you. I've gotten to this so much that I kind of just lazily do that sometimes with my limits. So now, real quick, what does all this mean? I'll erase some of this stuff. You don't need all that. But it's good for context for you know how to write this, because I'm sure when we're grading these, we're going to see some really creative new limits we've never seen before. All you're doing here is you're always going to write out the limit like this right here. Always write out, oh, you can't see me. Write out that limit just like that, okay? X approaches something, okay? So for what we're doing now, we're doing end behavior. We're just doing positive infinity and negative infinity for today. That's it. And that's going to equal either a positive infinity or negative infinity, all right? So let me put this together right here for you. So use limits to describe the end behavior. So this is already pre-written for us, which is totally awesome. That's not always be pre-written, but we're just first learning it. So the limit of this function as x approaches negative infinity. Negative infinity, that's going to be the left. That is left end behavior, okay? If we're looking at this, if I'm counting, that's a power 1, that's a power 1. We have degree 1, 2, 3, 4. We have degree 4. I've counted 4. And my a value is going to be negative 1, which is negative. So I have some sort of even degree function that looks something like that. So my left end behavior is going to be equal to negative infinity. And if we're going out to positive infinity, that's how I know, by the way. Let's go to this right here. That's going to the right. Positive infinity on the number line is to the right. This is going to give me also a negative infinity value. Because again, we are degree 4, so the left and the right are going to have the same end behavior. All right, have I confused you yet? No? Okay, last thing right here. Okay, let's talk about how to draw now our zeros, or our roots, or our x-intercepts. You notice those are the same thing. Roots, zeros, x-intercepts, all the same thing. So if we have a single root, it's just going to cut through the axis, the x-axis. So what that looks like, well, if I have x equals 3 here, so I'll go out to 3, 1, 2, 3 tick mark. Okay. I have a positive right end behavior. So positive infinity for right end behavior. So I'm going to be up here. I put a little C right there saying, hey, I just cut that. All right. That's a cut. It looks like a linear function. It's going to go through the x-axis as a linear function. Next one, double roots. Kind of looks like a parabola. We call this bounces. This is not going to go through the x-axis. It's actually going to bounce off of it because it's an even root. Okay, every even root bounces of some sorts. Every odd root goes through the x-axis. All right, so a double root, which is right here. We are tangent to the x-axis. That's another way of saying it. You do need to know that. It's tangent to the x-axis. And it bounces. So in this case, we have our root here at 4. So this is x equals 4. 1, 2, 3, 4. Put a B for bounce. Helps me out. My end behavior is going to be negative infinity to the left. Sorry, why did I say left? I'm making too many of these videos. Negative infinity, this is to the right. I always do the right first. And so it looks like this. Just bounces off that line. And then a triple root flattens out. It's also looks like a point of inflection, POI, point of inflection. Again, if you either unmute it. Can't unmute it. So here we go. So this one right here, this is going to be an x equals 2. I don't know why we got so complicated on the basic notes here, but this is x equals 2 as a root. So 1, 2. And we are positive and behavior on the right side. So what we're going to do is we're going to draw like half a parabola. This one's concave up. Draw another half parabola the other way, so it's concave down. So we change concavity. Okay, that's what it looks like to flatten out. I'll put a little F for flatten. All right, super simple. Let's take all of this fun knowledge that we just learned and apply it right here. Okay, I'll go ahead and sketch the graphs of the following. Okay, so for f of x, this is for a. We have two distinct roots. We have x equals 1, and we have x equals -3. All I'm doing is I'm taking each factor, setting equal to 0. Okay, so at x equals 1, I'll go out 1 tick mark. I'm going to put a C up there that helps me out, the drawer of the sketch here. I know that's a cut. And then at 1 to -3, put a dot right there. Put an F for flatten. Okay, this is a even degree, by the way. So this is even degree. How do you know that, coach? Because I can count. 3 plus a 1 right there gives me 4, which is even degree. The coefficient is going to be positive. So we're going to have a positive infinity right end behavior. So I start from up here, and I'm just going to cut. And then I have to go through the flatten as well. So I'm going to turn back around. Looks like I'm going to have a local min. And I'm going to flatten like this. And behavior looks perfect to me because, again, it's even degree. It's going to go on the same end behavior. So it's going to be positive infinity both sides. And that's it. Super simple. Knowing how to do this is going to really help you out with a lot of the stuff that's coming up. You can even see the day 2 notes starting to creep up here. Next one. Well, this is a x equals 0 root, or 0. And this is x equals, again, -3. At x equals 0 right here, it's going to be a b for bounce because it's degree 2. At -3, 1, 2, 3, that's going to be a cut because it's got a degree 1. By the way, this is an odd degree because I can count. 1 plus 2 is 3. It's odd. And we're going to have a negative right end behavior because the coefficient is negative. So we're going to start down here. And what we're going to come up, we're going to bounce off the origin. And we're going to turn it right back around to cut through that guy right there. Any questions? It's a video. All right. Last one. I'll do a different color for this one. I'll do magenta. H of x. Got quite a few things going on here. I got x equals -2. By the way, that's a cut. I got x equals 5. That's going to be a flatten. I got x equals -9. That's going to be a bounce. So let me go ahead and put all this stuff on here. So -2, 1, 2. It's a cut. 5, 1, 2, 3, 4, 5. It's going to be a flatten. And then -9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Close enough, right? And that's going to be a bounce. We are even degreed. 2 plus 3 plus 1 is 6, which is even. So even degree. Our right end behavior is going to be positive. Nothing tricky here. So we're going to start up here. And we're going to flatten. That was just awful. I wonder if there's an easy way to redo that. Friendly reminder, use pencils when you do notes in math. So we're going to flatten here. Turn it back around to cut through. And then we're going to bounce. If you notice the two end behaviors match up. That's it. These are long notes, so I'll be done. Okay. Again, Coach Biden Bar, like, subscribe, have all that, do all the fun stuff.